In section 5.2, we're continuing to look at inverse trigonometric functions. For this first example, we're looking at composition of functions. So as you can see, we're taking the sine of the inverse tangent of 1/2. So whenever you have mixed functions, they don't undo each other. Like if this was the sine of the inverse sine of 1/2, the sine and the inverse sine undo each other. But that doesn't happen here. So what we're going to have to do is we're going to have to evaluate first the inside function and then input that value into the outside function to evaluate it. So let's first evaluate the inverse tangent. So that means, let's see, we want to find the tangent of theta that is equal to 1/2 on the interval from -π/2 to +π/2. Oops, and that should be just less than, not less than or equal to. Okay, so since tangent is greater than 1, or since tangent of theta is greater than 1, we know that theta has to be in quadrant number 1. And since tangent of theta is equal to y/x, and in this case it's 1/2, we know that y/x is going to equal to 1/2. So therefore y is equal to 1 and x is equal to 2. So here we are, we're going to be in quadrant number 1. With a y value of 1 and an x value of 2. So we'd be somewhere kind of like here. Say this is 2, 1. And if we think all the way back into chapter 1, chapter 2 time frame, we need to be able to find out what this value is, the hypotenuse, because we want to find the sine eventually. So what we need to do is we know that the radius squared is equal to x squared plus y squared. And here our x is 2 and our y is 1. So our radius squared is going to be equal to 2 squared plus 1 squared. So our radius squared is 4 plus 1 leaves us with 5. So therefore our radius is the square root of 5. Now we can't find the exact value of the inverse tangent of 1/2. We don't have a way to do that. We could do it with a calculator, but that's not going to really help us. So what we do here is now we know enough information. It helped us to figure out our triangle. And so we know that this side is a length of 2, this side is a length of 1, and our hypotenuse now is the square root of 5. So we just need to find the sine of that triangle, or the sine of that angle, whatever this reference angle in here happens to be. So in order to do that, we are going to find the sine. The sine is opposite over hypotenuse. So the sine of, the inverse tangent of 1/2 ends up being our y value, which is 1, over our r, square root of 5. And we have to rationalize that. So we multiply by the square root of 5 over the square root of 5 to get an answer of the square root of 5 over 5.
Example B. So again, we're going to have to evaluate the inside function before we can evaluate the outside function. And once we have evaluated this inside function, then we can substitute whatever that value is into the inside to solve our outside function. So first, we want to solve sine of theta is equal to -1/3 on the interval from -π/2 is less than or equal to theta which is less than or equal to pi over 2. Because that is our interval on which the inverse sine is defined. Since this is a negative value, we know that theta is in quadrant number 4. Because sine values are going to be negative in quadrant number 4. We also know a few things. Because we know that sine of theta is negative 1/3, that tells us that the y value is going to be negative 1, and our r value is going to be 3. So we can think about this or draw this out in quadrant number 4 here. We know that our r is going to be 3, and our y is going to be negative 1. So if y is negative 1, we need to find x first. And we know way back from chapter 3 that x squared plus y squared is equal to r squared, or r is equal to the square root of x squared plus y squared. So we have x squared plus negative 1 squared is equal to 3 squared, or x squared plus 1 is equal to 9. So x squared is equal to 8, and therefore x is equal to the square root of 8. And the square root of 8 is the square root of 4 times the square root of 2. So therefore x is, the square root of 4 gives us 2, and the square root of 2 stays the same. So we now know that x is at 2 square root of 2. So if we think about this in terms of our unit circle, we know that we're at an ordered pair of 2 square root of 2 and negative 1. So we're going to be somewhere about here. And actually, let's draw just a standard unit circle. It'll make this a little bit easier. So if we have our unit circle here, and we're going to have an angle that started on the positive x-axis here and rotated and ends here in quadrant number 4. And it's going to have an ordered pair here of 2 square root of 2, negative 1. So our radius is 3. This distance is 2 square root of 2. And then this distance is negative 1. Not exactly drawn to scale, but you get the idea. So now we need to utilize this angle to find the cosine. Well, cosine is always x over r. Therefore, the cosine of theta is going to be the square root, or 2 times the square root of 2 over 3. And therefore, that is going to be the solution to our problem. We end up with the cosine of the inverse sine of negative 1/3 is equal to 2 square root of 2 divided by 3. So for example C, first you had to utilize cosine. We know that cosine is on the interval, or inverse cosine is on the interval from 0 to pi, and so therefore cosine of theta has to have a value of negative 1/3 on that interval. and cosine is negative in quadrant number 2. So therefore, we know that our angle is going to be in quadrant number 2. And we use the fact that cosine is x over r to know that our radius is going to be 3, our x value is going to be 1, and using the Pythagorean theorem or the equation for the radius gives us a y value of 2 square root of 2. And if you don't know why it was 2 square root of 2, it's the same reason it was in part B. Then, now we need to evaluate tangent for this angle. And we have the tangent value, or we have our x and we have our y. Tangent is y over x. And so here we have tangent of theta is going to be this 2 square root of 2 divided by -1. And I notice that I forgot a negative in here. And so therefore, the tangent of the inverse cosine of -1/3 is going to be -2 times the square root of 2.
So, when you're dealing with inverse secant, inverse cosecant, or inverse cotangent, you just need to think about their related reciprocal functions. And then you'll know a little bit about the domain and the range. When we look at the inverse secant, y equals the inverse secant of x, that means x is equal to secant of y. Or what angle would give us that secant value? Where our x value is going to be greater than or equal to 1, the absolute value of it. So essentially, our x values have to be between -1 and +1, and our y value has to be between 0 and pi. That makes sense because remember, secant's reciprocal function is cosecant, cosine. Now, why can y not be equal to pi over 2? If you remember back to secant, 1 divided by the cosine of pi over 2. The cosine of pi over 2 is 0. That's where our asymptote is located, or our undefined functions, so it's never going to be equal to that value. Inverse cosecant, well, remember, cosecant is related to its its reciprocal function, which is sine. So, y equals the inverse cosecant of x means that x is equal to the cosecant of y, where our x value is greater than or absolute value of our x value is greater than or equal to 1, or essentially between -1 and +1. And our y value has to be between -pi over 2 and +pi over 2, and it cannot be equal to 0. That makes sense because inverse sine is between -pi over 2 and +pi over 2, and this is where the cosecant is undefined. For cotangent, Riley, stop. Okay. Our inverse cotangent of y equals inverse cotangent of x means that x is equal to the cotangent of y, where we go from -infinity to +infinity, and for our x values, and from 0 to pi for our y values. So let's look at an example. We want to find the exact value of the inverse cosecant of 2. So, one way to think about this is to think about its reciprocal function. So, first off, we want the cosecant of theta to be equal to 2. On this interval from -pi over 2 to +pi over 2, and theta cannot be equal to 0. So, really, think about what angle gives a sine value of 1/2. So we want our sine value of theta to be equal to 1/2. Since we want our sign value to equal positive, well, that happens to be in quadrant number 1. And so where does that occur? Well, the sign value to be 1/2 is when we have a reference angle of 30 degrees. So in radians, that would be pi over 6. So therefore, the inverse cosecant of 2 would be equal to pi over 6. And why did I think about the sine function? Because that is the reciprocal. So if I thought about this as 2 over 1, and I took the reciprocal of that function, I would end up with 1/2.
Part B looks at the inverse secant of the square root of 2. First off, we want to think about secant. Secant has to be greater than or equal to 1. And also, it's going to have a output between 0 and pi, and it can never be equal to pi over 2, because that's where the asymptotes, or that's where our secant function is undefined. Or another way to think about this is we want to know what angle theta will give us a secant value of the square root of 2 on the interval from 0 to pi, and theta can also not be equal to pi over 2. We know that theta is going to be in quadrant number 1. Since this is dealing with quadrants 1 and 2, just like cosine. Remember, cosine is its reciprocal function. And so since we know that it's in quadrant number 1, that comes from the fact that the secant value is positive. And so we want to essentially think about what angle the cosine of theta is equal to 1 divided by the square root of 2, that reciprocal. And that reciprocal, if we were to rationalize it, is going to be the square root of 2 over 2. So we're looking for that angle that has a square root of 2 over 2. Since we're in quadrant number 1, I'm just going to focus here on quadrant number 1. If we had our unit circle in here, we want that angle in which we have an x value of the square root of 2 over 2. Our hypotenuse is going to be 1. And we know that this must be square root of 2 over 2 from all of our use and work with the unit circle. Therefore, this angle in here has a reference angle of pi over 4. So in this case, theta would be pi over 4. And so we can say the inverse secant of the square root of 2 is equal to pi over 4.